Welcome dear students. Today we will try to understand the meaning of a dimension of a physical quantity. So we have studied earlier there are 7 fundamental quantities through which we can derive the units and possibly the dimensions of all other quantities which are called derived quantities, derived physical quantities. So what are the 7 fundamental quantities? They are respectively length. For length we state L, for mass we state M, for time we take T, for current we take A, for temperature we take K, for luminous intensity we take CD, candela, for amount of substance we take mole. So whenever we will be asked to find out the dimension of a derived quantity, we will try to find that in terms of these things. Now the second thing is that what do we mean that by the dimension of a physical quantity? So the definition is that they are the powers or exponents to which the fundamental quantities must be raised to represent the quantity completely. What do we mean by that? Let's take an example. We know that density is defined as mass per unit volume. Mass per unit volume. Now for mass, I have written here the dimension is m, so I will write m. And the volume, for volume, we know volume is the cube of length, and for length we have taken the dimension L, so it will be L cube. So finally we can write the dimension will be of density will be m to the power 1 L to the power minus 3. Though the convention is we always try to write the dimension in terms of m, L, T at least. So we can also write T to the power 0. So here we have find the dimensions of a physical quantity which are 1, minus 3, 0. So we can see that these are the exponents. 1, minus 3, 0, through which mass, length and time has to be raised to represent density. So this is the example. Also another example we can take is like angle. For angle, though we will find these dimensions again, but still for angle we know angle is basically defined as arc per unit radius. So for arc is a length, nothing but a length. We know this is the radius and this will be an arc. So this is the angle theta. So theta is defined as like arc per unit radius, so S by R. So what will be the dimension of angle? It will be simply dimension of arc is length and radius is also length. So they will get cancelled out and we are left with 1. So it is a dimensionless quantity. So for dimensionless quantity, the dimension will be 1 always. 1 means there will be no dependency on the fundamental quantities. Okay. So next thing is that what do we mean by dimensional formula? So dimensional formula is the expression showing how and which fundamental quantities represent the dimension of a physical quantity. So we will try to find many dimensional formula one by one, which are to be some of them are to be memorized to solve the advanced problem that will be appearing in exam as well as other competitive exams. Okay, so at first we have found the density. Second is like speed or velocity. Like speed, example 1, it is speed or velocity. We know speed and velocity is kind of same quantity, but their dimension are same, but one is a scalar, another is a vector. So speed is defined as distance traveled per unit time by rate of change of distance, and velocity is defined as the rate of change of displacement. So it is basically distance upon time. So distance, the dimension of distance is L, time is t, so it will be simply Lt minus 1. Next is acceleration. For acceleration, we know what is the definition of acceleration. It is the rate of change of velocity. It is a vector quantity, it depends on velocity. So rate of change of velocity, and that means it is change in velocity by change in time. So change in velocity itself is a velocity, so its dimension will be of that of velocity, so it will be Lt minus 1 divided by change in time, that dimension will also be time. So we are left with Lt minus 2. So the dimensional formula of acceleration will be Lt minus 2. We will always put the answer in a third bracket because this is a convention. Okay, next is momentum. Momentum is defined as mass into velocity. We know from the Newton's first law that if you do not put any external force on an object, the quantity that remains conserved during the motion is momentum. So the dimension of momentum will be mass to the power 1 because there is a mass, and velocity, for velocity we have already found Lt minus 1, L to the power 1 and T to the power minus 1. So this will be its dimensional formula. Next is force, very important example, force. What will be the dimension of force? We know force is basically mass into acceleration from Newton's second law. Though this is the original formula is dp dt, but taking the non-relativistic approximation, we can say that force equals to mass into acceleration. And for mass it is 1 and acceleration we have already found Lt minus 2. So m to the power 1, L to the power 1 and T to the power minus 2. Okay, next is work. So what will be the dimension of work? We know work equals to force into displacement. Though F dot R, but we have not studied yet vector multiplication or scalar multiplication. So work done will be force into displacement. And for force we have found dimension is mLt minus 2 and displacement is L, so it will be mL square T to the power minus 2. Third bracket. Next is energy. Now we know that what is energy? Energy is defined as the capacity to do some work. Also, so that means work and energy are of same dimension. That is m, there was a 1, m to the power 1, L square T to the power minus 2. These things are to be remembered because in numerical problems these things will be used. Okay, next is power. So for power we know power is defined as the rate of doing work or work done per unit time, simply put. So it will be work done per unit time. So for work done, it is the dimension was m L square T to the power minus 2 divided by time was t. So it will be m L square T to the power minus 3. Okay, next power, and next pressure. So what will be the dimension of pressure? Pressure is defined as the actually thrust per unit area or force per unit area, fundamental perpendicular component of force per unit area, that is pressure. So basically force per unit area, and force dimension is mLt minus 2 and area is basically L square. So it is m to the power 1, L to the power minus 1, T to the power minus 2. Third bracket. Okay, so next is torque, moment of force. Some of you have studied it and some of you have not yet. So what is torque? Torque is defined as It is basically, it was defined, if you have studied in ICSE, torque was basically uh, the distance from the it is the force applied into the distance between the actual real formula is basically it is R cross F. We will study it in the rotational motion chapter, but for now it is R cross F, that is it is length into force mlt minus 2, so it is m l square t minus 2. Now there is a contradiction, actually similarity. In torque the formula is m square t minus 2, in energy it is also same, in work it is also same. So we can see that for different quantities, different physical quantities, the dimension can be same. Okay, next is a very important example that is often asked in exam. It is the gravitational constant. Gravitational constant G. So to find the dimension of a constant or anything, what we do is that we at first try to find a formula in which it appears and in which we know the dimension of all other quantities that has appeared in the equation. So we know that the gravitational force between acting between two objects is given as the formula given as like G m1 m2 divided by r square r cap, and there is a minus sign. So forget about this cap, but the if I take the scalar form, this is the formula, and from it we separate out the G in the left side and all the things on the right side. So we are left with, also we neglect the sign right now, so we are left with f r square by m1 into m2. Now if we put the dimensions of these quantities, because I have already said that you have to remember these dimensions, so it is basically m l t minus 2, and it is length square, and it is mass square. So if I cancel out, we are left with m to the power minus 1, l to the power 3, t to the power minus 2, and this is the dimension of G. So this all shows how we can find out the gravitational constant of a the dimension of a gravitational constant. Okay, so there are many more dimensions that you have to remember, which are written in your books. So try to practice those dimensions, finding those dimensions, and also their units are also given in terms of the units of fundamental quantities, which depends upon the dimension. But I am not talking about that. Now we will try to solve some questions which are likely to be asked in your exam related this topic. So the first type of question is, name the physical quantities whose dimensional formula are as follows. So the dimensional formula will be given to you, and you will be asked the quantity of which this dimension is given. So for which I have told you that you will have to remember the dimensions of some minimum number of quantities, so that you can find these dimensions. So let us take one by one. So the first is given as m l square t minus 2. So m l square t minus 2. So it can be written as m l t minus 2 into L into L. So this thing is basically for the dimension of force. So it is force, dimension of force, and this is length. So force into length. That means force into displacement, and which is work done. So the dimension is of work Also the dimension of work is same as energy, and another thing we have seen, but okay, so work and energy, and another is torque. So three quantities have the same dimension, so you can write three of them also, because these three have same. But for the second question, it is ml square p minus 3. So ml square t minus 2 we have already done that. So ml square t minus 2 divided by t basically. So this is the dimension of work, and you are dividing this with time. So work per unit time, it is basically our power, dimension of power. Okay, third question, m t minus 2. So it is basically, it can be written as mlt minus 2 divided by length, right? And this is the dimension of force. This is force divided by length. So this is new quantity to you. This is called surface tension. Force per unit length, it is surface tension. Try to remember it. Often asked, often appears in the exam. Force per unit length. Next is m l minus 1 t minus 1. So this is basically lt minus 1. Okay. So mass per unit length, it is basically ml minus 1 t minus 1. So it can be written as maybe, it can be written as m lt or mass by lt. Okay, so this quantity is a new quantity. This can be written as m l t minus 2 divided by L square into T. So not into T, it is L T to the power minus 1. T to the power minus 1. So this is basically force divided by here L square is the dimension of area, force per unit area, and T to the power minus 1 is dimension of velocity gradient. Velocity gradient means change in velocity per unit distance. So dv dx it is kind of. So area into, it is velocity gradient, or vg I can write for now. Velocity gradient. So force per unit area per unit velocity gradient, it is the dimension of viscosity. So it will be studied in the chapter mechanical properties of matter, in mechanical properties in fluid mechanics. So the corresponding formula is like F equals to minus eta a dv dx, but forget that for now. So this is a unique dimension of viscosity. Another is m l minus 1 t minus 2. So this is what? This is basically, there is a formula. Okay, so there is a relationship between stress and strain. Two quantities I have not talked. So what is stress? The dimension of stress is defined as, of that same as pressure, force per unit area. So its dimension is basically force per unit area. So of that of pressure, so force means m lt minus 2 per unit area is L square. So its dimension is m to the power 1 L to the power minus 1 T to the power minus 2. And strain, for strain it is change in dimension by original dimension, change in length by original length. So it is change in length, which is the dimension of length, by original length. So this is dimensionless. So stress dimension m to the power 1 L to the power m to the power 1 L to the power minus 1 T to the power minus 2, and strain is 1. So if you divide stress by strain, you get the same dimension as asked here. So this is the dimension of Young's modulus. Young's modulus. So if I can write here properly. So it is basically, question was m L minus 1 T minus 2, and so it is m L T minus 2 divided by m L to the power minus 1 T to the power minus 2 divided by 1. So stress by strain, it is Young's modulus. Young's modulus. So the first question is done. You have found out all the dimension of physical quantities. The second question. So next question is asked as deduce the dimensional formula for the following quantities. So physical quantities are given, which you will have to find. So we try to find one by one. First is gravitational constant. We have found that formula for gravitational constant is F equals to minus g m1 m2 by divided by r square. So from here g equals to neglect the sign right now. So f r square by m1 m2. Okay, so write down the dimension of each quantities. It is m L T minus 2 into length square divided by m square, because product of two masses. Cancel it out. So and you are left with basically just do the size L square. So we are left with m to the power minus 1 L to the power 3 T to the power minus 2. That is the dimension of gravitational constant. Okay. Next question. Young's modulus. Young's modulus we have already found out, so I can neglect it. Next is coefficient of viscosity. Actually, we have already found out that also, but from formula, how can we find out that? The formula is F equals to minus eta A dV dx. Okay. So here eta is the surface tension, A is the area, and dV dx is the velocity gradient, and F is the viscous force. So from here, eta is the coefficient of viscosity, so eta equals to, neglect the sign also. So eta equals to F by A dV dx, velocity gradient, and force is m L T minus 2. Area is length square. Velocity is basically Lt minus 1. And x is length gets cancel out. Okay, so here also another cancellation, t to the power minus 1 t to the power minus 1. So we are left with mt minus 1. mt another L, so m L to the power minus 1 t to the power minus 1. And we have already found out that earlier, mt minus okay. Second question. Okay. Third question we have done. Next is fourth question, Planck's constant. Very important. So Planck's constant, I like to do it. So third question. Okay. So third question, Planck's constant. So a very empirical formula where Planck's constant emerges is E equals to h nu. which we will learn in chemistry as well as in physics, in atomic physics basically. So E equals to h nu, where E is the energy, h is the Planck's constant, nu is the frequency. What is this? What do we mean by this? It will be studied in the chapter, but okay. So here nu equals to, h equals to E by nu, energy per unit frequency. So the energy, dimension of energy is ml square t minus 2, and the frequency is basically okay. Okay. So energy equals to h nu, implies h equals to E by nu equals to m l square t minus 2 by frequency. Frequency is what? 1 by time period, so 1 by t, so t to the power minus 1, so t to the power minus 1 left, so m to the power 1, l to the power 2, t to the power minus 1. So this is the dimension of Planck's constant. 4 is Boltzmann constant. Now we know real gas equation is PV equals to nRT. No, it is actually ideal gas equation. Real gas equation is represented by van der Waals equation. So R is the Boltzmann constant here. So take R at the left side and all the quantities that are other. So it becomes PV by NT. So for pressure is basically force per unit area. So force per unit, we also found out earlier, force is ml t minus 2 by area L square. So m L minus 1 t minus 2. Volume is L cube by this is number of mole, so mole, and time is basically t. Now this is thermodynamic temperature, so it is T. It is K. It is taken as K. So mole K. Okay, so the final dimension is basically m to the power 1, L to the power 2, T to the power minus 2 per mole per Kelvin. Okay, per mole per K, not Kelvin, per K. So another last one is not last one. Okay, next is charge. For charge, I can write Q, charge. Charge formula is current into time. So current dimension was, we have taken as I, or in some books you can see there is written A. So AT or IT. So I into I to the power 1, T to the power 1 dimension. Okay. Next is, last one is resistance. So we know V equals to IR. So R equals to V by I. So V is the potential, and potential is potential energy per unit charge. We will learn it later, but potential energy per unit charge. So dimension of energy m L square t minus 2 per unit charge. Charge is basically I into T, and divided by current. Current is I. So it is basically m to the power 1, L to the power 2, T to the power minus 3, I to the power minus 2. So this is the dimension. Okay. This question is done. Next question. Another kind of question that is asked is that sometime you will have to find out the dimension of a fundamental quantity, taking the derived quantities as fundamental. So you have to express the dimension of a fundamental quantity in terms of derived quantities. Now this is a tricky question, but it is actually easy. You have to actually, in these cases, you have to know the formula in which all the quantities appears or somehow related. So here it is given velocity, time and force. So we actually know that from Newton's law, force equals to mass into acceleration, okay, and acceleration is basically change in velocity by change in time, so velocity by time. change in velocity by change in time. Change, so delta by delta. Okay. Now, so mass can be written as force into change in time divided by change in velocity. Now, take the dimension of velocity as v, time as t, and force as f, and write them down here. So it becomes f into t by v, which has become finally f to the power 1, t to the power 1, v to the power minus 1. This is the dimension of mass in terms of these quantities. Okay. Last question, same type. Taking force, length and time chosen as the fundamental quantities, find the formula of density. So density, as we know, density is basically mass per unit volume, so m by v. Now mass is obviously represented in force, time, velocity. So what are the quantities given? Force, length and time. So force, length and time, these are the quantities we will use. So how can we do that? So for volume it is L cube because L is permitted here. For mass we have found that it is basically f to the power 1 and t to the power 1, but velocity to the power minus 1, and velocity is not allowed here, but velocity is lt minus 1, which are allowed. So take lt minus 1 and its power is minus 1, so minus 1, and solve it. So f to the power 1, t to the power 1, l to the power minus 1, t to the power plus 1 divided by l cube. So basically it finally becomes f to the power 1 minus 1 minus 3 minus 4, l to the power minus 4, t to the power 2, so t to the power 2. So this is the expected dimension. Okay, so these are the questions which are to be asked from this portion of dimension. The basic concept of dimension and dimensional formulas. In the next class, we will try to understand, incorporate these ideas into a thing that is called dimensional analysis, the process, which is a very important process. So for today's class, we can end now.